Okay, in this one we will be covering diffraction, polarization, and the Doppler effect. Okay, so in the first scenario, the diffraction that we're going to talk about, this is simply when a wave bends around an obstacle. So here we have an obstacle, and it occurs when waves, like in blue, like these are water waves encountering this obstacle, when they bend around the obstacle. Okay, when when a wave diffracts, it does not change the frequency of the wave. All right, it doesn't change the wavelength of the wave. The wave just bends around the obstacle. This is why you can hear around corners. Okay, like you don't need to be in direct line of sight of somebody to hear them. Diffraction also, if the wave is larger, it has a larger wavelength, it is much easier to diffract around obstacles. So we have scenario 1 here and scenario 2 here. It's much easier for the larger wavelength to diffract around the obstacles. Alright? This is why you can put subs in the back of your car and not have to worry about them. Tweeters, on the other hand, you have to put in the front of your car because they have to be directionally pointed toward the person that you're trying to reach. Next we have polarization. Polarization is when we limit light to one direction. Alright, so under normal circumstances, light is coming in all these hodgepodge of directions, a kerfuffle, if you will, of directions. It's just all going every which way it wants to. Okay? If you wear sunglasses that just dim it, you'll still have this hodgepodge. It's just going to still go every which way, but it'll be less of it. So this is what will happen if you just dim it. But with polarization, what you do is you create slits, tiny slits in a film, and these tiny slits allow only light that's traveling in a certain direction to go through. So we have polarization only in one direction. Okay, so that is that is how polarization works. Light being forced to go only in one direction. On an afternote, if you have one film pointed this direction and then the next film you point this direction, obviously the light can't get through, so you will black out the light, right? You won't be able to see anything through it. Okay, so that's polarization. Then we have the Doppler effect, and the Doppler effect is caused by a sound being emitted by a moving object. All right, or a wave being emitted by a moving object. So let's say under normal circumstances, this ball puts out a wave that looks like this. It's putting out sound waves that look like that. Now, what happens if that ball is thrown towards you? Well, the wavelength shrinks. Okay? It is a perceived shrinking of the wavelength. And what you hear as the ball comes towards you is the frequency goes up, if you're here. Okay? On the other hand, if you're here and the ball is moving away from you, then what you perceive is a increase in the wavelength. So the wavelength in the first option, the frequency goes up and the wavelength goes down. In the second option, the wavelength goes up and the frequency goes down. Now, this is a perception. It's not really what's happening, but it's what you perceive as happening because of the Doppler effect. Were you to be like riding on the ball, you would still hear the same amount of sound because you're going the same speed as the ball. Okay? The important thing about the Doppler effect is that it has to be a very decent percentage of the speed of the wave in order to be noticed. So for instance, for sound is 343 meters per second. So normally we can perceive this at like fairly low velocities, like 5 meters per second or 10 meters per second. But Doppler effect does occur in waves like light. But we don't perceive a shift in the frequency of light, the color of light, when objects are moving, because the speed of light is 3 times 10 to the 8th meters per second. And so to get like 5, we said it would work in 5 meters per second with sound roughly. That's going roughly 1.5–2% the speed of sound. In order to go 1.5–2% the speed of light, you would be needing to go 5 to 10 million meters per second, which is just not feasible. So that's the reason you don't see the Doppler effect. It does exist, it's just not easily viewed.